Okay, students. I think my screen is visible now. Now we can start the presentation. Uh, so once again, welcome you all to this live session 8. This live session is of Physics of Renewable Energy System, a NPTEL course taught by Professor Amrish Chandra. This is from Department of Physics, IIT Kharagpur. And this course is taken up by me. I am a PMRF scholar at IIT Bombay. So I apologize for the this some issues which happened with the Google Meet. I think they were not around to share the screen, so I sorted it out. So I think it's visible and I'm audible to all. Okay, nice. So I planned this session like we will do revision of the previous live session, the previous session of week 7. Then we will go on solving some conceptual questions. Then there are some numericals also this time. So I would expect you all guys to solve these numericals by yourself. And we will solve this numericals in the class itself. And if there are any queries, any questions, or if you think that numericals are getting hard, you cannot solve it, so just ask me the question. I am always available to solve you guys, to assist you guys in solving the numerical. So if you see the previous live session, we mostly talked about the different electrochemical, electromechanical things like pseudocapacitors, battery, ADLCs, supercapacitors, double layer capacitors. So basically, we talked about pseudocapacitors. So what are pseudocapacitors? So they store electrically charge, electrical charge, and transfer this electrical charge between electrodes, and instead of a dielectric like we have in capacitors, we have electrolyte here in pseudo capacitors. So why pseudo? What is pseudo? Pseudo is something which behaves like a capacitor. So where do we use electrolyte? We have electrolytes in batteries. So that's why these pseudo capacitors are highly energy dense. They can store a lot of energy, lot of power in them. So that's why they are called supercapacitors, and they can store a lot of energy in them. And we talked about battery. Battery, what is battery? So battery is just a device which can store electrical energy in form of chemical energy. So whenever we require electrical energy, so that's why the reaction, chemical reaction takes place inside the battery, and that gives us electrons. Okay, so this is the simple concept, simple difference between a pseudocapacitor, capacitor, or battery. Then we talked about the electric double layer capacitance. So these are double Helmholtz layer, and there is a charge of double layer actually. So you will read more about it when you go through the slides. Very beautiful concept explained by professor. Then we solved a conceptual question based on Gray-Chapman model. So this model actually describes a rigid charge surface, and it says that in near adjacent of a rigid charge surface, the concentration is actually more, and when we move away from this rigid charge surface, the concentration of oppositely charged ions starts decreasing. So this is a normal concept, but you have to actually grab this concept very with uh, like simple. If we have a capacitor, or if we have an electrode with positive charge, so what it does is if there are any negative ions in the electrode, then most of the negative ions will be found near that positive electrode. Okay, and that negative ions concentration will go on decreasing as we move away from the electrode. So that is the main concept of Gray-Chapman model. And then we learned about the Coulomb efficiency. So Coulomb efficiency is basically discharging a charging cycle. It is relating the discharging a charging cycle. So it refers to the ratio of discharge capacity after the full charge and the charging capacity of the same cycle. Okay, so when does a cycle occurs? A cycle is only said to be completed when it is fully discharged and then fully charged. So that constitutes a single cycle. Okay. Now we move to the next slides. We will start the discussion for today's session. Let me check if anyone wants to join. I think no one. So we can start. So the first question is, consider two reactions, reaction 1 and 2, and having activation energy EA1 and EA2. And if the graph of log rate constant versus temperature inverse is plotted, then what will happen? Slope 1 is greater than slope 2. Slope 1 means slope of reaction 1. Okay, slope 2 is slope of reaction 2. So first you grab this concept, actually how we can determine the slope. Okay, so let me tell you, if this is what does this say, log rate constant, let it be log k rate constant, okay, versus 1 upon temperature graph. So that's what it is saying. So assume it to be x, okay, and assume it to be y. So if we plot this graph and EA1 and EA2, so you know how do we relate rate constant with activation energy? K is directly proportional to activation energies. Okay, you know by Arrhenius equation. What is the Arrhenius equation? K, that is rate constant of the reaction, 3 exponential factor into exponent to the power minus activation energy upon R, which is universal gas constant, and T. And mind it, the T is in Kelvin, not in Celsius. Okay, so whenever we use any formula, be sure to use the parameters or values in their SI units. So what is the SI units of unit of temperature? It's Kelvin, not Celsius. Okay. So A is, you see, whenever we increase EA, the value of K will increase. So that means if we have two activation energy, EA1 and EA2, if the graph of log rate constant versus temperature inverse is plotted, so if we plot this graph, log rate constant versus temperature, 1 by temperature. So this will be something like exponential graph or something, but you will see that actually with the temperature, as we increase the temperature values, like if we plot it here, so rate constant value will decrease similarly. So what does this mean? This rate constant value, as we go on increasing the temperature, the rate constant value will go on decreasing. Okay, so this will be like exponential curve or something like this. So for if we have activation energy, two reaction of activation energy EA1 and EA2, if EA1 is greater than EA2 for two reaction, then certainly this slope of the first graph will be more than the slope of 2. So the correct answer is A. Okay, slope 1 is less than 2, no, because we are assuming that EA1 is greater than EA2, and it cannot be equal because values are not equal. Will depend on the reaction temperature. It can depend on the reaction. It cannot be said to be dependent on reaction temperature, because we are plotting the graph with temperature only, the temperature inverse. Okay. I'm moving to the next question. The current versus voltage profile within one potential window of RGO based electrode of active mass 1.5 milligram showed area under the curve as 26.3 milliampere volt. So at a scan rate of 25 millivolt per second, what should be the specific capacitance of RGO? Okay. So let me see if anyone wants to join. No. if we see this question, first we have to understand this question. So this is a numerical question. You have to look after it very clearly, that what are the requirements of this question. So this question is that if current versus voltage profile, okay, within 1 volt potential window. So if you plot a current versus voltage profile, this is I and this is voltage profile within a potential window of 1 volt. So if we are keeping marking 0, 0 0.2, 0 0.4, 0 0.61 and window of Rg0, the base electrode of active mass 1.5 gram. So what is the active mass of electrode? 1.5 gram. So the area under curve. So there will be some curve like this, charging, discharging or something. So what it is saying, the area under the curve is 26.3, and mind it, it's milliampere volt. Okay, and at a scan rate of 25 millivolt per second, what should be the specific capacitance? That is asking capacitance. So what we got, the capacitance is related to the area under the curve. So when we have an area, something of curve, some unnatural curves, unnatural, you can't say, some curves with degree of polynomial we don't know. Okay, so for these type of curves, how do we take the area? So we actually divide it into infinite loops, infinite elements, and then integrate the whole elements. Okay, so we get the area under the curve. So that is done here. Integration of IdV upon scanning rate into voltage, and divided by 1 by 2m will give the capacitance, the specific capacitance. So why it is divided by m? So first see the word specific. You have seen in the specific volume, volume divided by mass is a specific volume. So that's what the concept is here. It is asking about the specific capacitance. So specific capacitance is the total area under the curve, and divided by the mass will give the specific capacitance. Capacitance divided by mass. Okay. So what is m here? M is active mass. I have written all the values. Mu here is scan rate, V here is cell potential, and IdV, area under the curve, you don't have to calculate, it is already given here, 26.3 millimeter volt. So one more thing, you don't have to convert these units into SI units. If you want, you can also convert, because the millivolt milli will cancel out. Okay, this area is in milliampere volt and the scan rate is also in millivolts again, so it will cancel out. So that's why that's how we put it here. The capacitance equal to 1 upon 1.5. So integration IdV is 26.3 into 26.3 upon what is the scan rate, 25 millivolt per second, and what is the voltage? Voltage is just 1 volt. Okay, and this is multiplied with 2. Now we calculate it. So what is this? 1 upon 3, 2 into 1.5 is 1 upon 3 into 26.3 upon 25. So we convert it, we calculate it, and the values comes out to be around 250 farad per gram. Okay, so see this, it is in per gram value. So you have to convert milligrams into gram. You have to divide it by 1000 per gram. So it will be multiplied by 1000. Now you see 26.3 into 1000 upon 25 into 3. Okay, so it's 26,300 upon 25 into 3, 75. So if you divide it, you will get this value. So that's how the specific capacitance is calculated. Got it? So one more thing here, one more concept is here, like IDV. So you have been given the area under curve IDV is 26.3 millimeter volts. What happens if this area is not given? So be sure you have to calculate it. Okay, you can always calculate it. Like let me do it for you. Let me solve a question also in which the area is not given. So let me draw a hypothetical curve like this. Okay, and this varies from 0 to 5. This is plus 1, this is minus 1. So this is volt, this is ampere. So how do we calculate this area? So if it is simple square, you can just calculate the area of this square and calculate the area of this square and take a mod of this area, because this will be negative, and add them. Okay. And if you don't want, you can always apply integration. So what will be the integration here? So what are the I dV? What is I? So I is also varying. Let just put it here. Just for this. Okay. So uh, I is 1 ampere. That is area under this curve, 1 ampere into dV. We don't know. Mu is constant. Scan rate, and this is V. So what is V? Where does this V vary from? Let's say it's 2.5. Okay, so 0 to 2.5. And this dV upon, if you integrate dV upon V, what you will get? You will get ln. So you will get ln V, and you put this value 0 to 2.5 there. And of course it is multiplied by 1, because 1 is the curve under which the area is seen. Okay, we may multiplied by 1. So if you put the value ln 2.5 minus ln 0, so ln 0 is 1, ln 2.5 will be something around 0.693 is for 2 now, so it will be around something 0.7 or something. So that's how this area is calculated. Okay. Now I am sure that you will be able to do this type of questions very easily. Now moving over to the next question. A supercapacitors. Let me see if anyone to join. Okay, nobody is joining. Now moving to the next question. So next question is also a numerical, good numerical, in which you will get to know about the energy density and power density, and how do we calculate these for especially capacitors. So when you read this question, first you have to understand the question. What the question say? It's a simple question, just big lines. You don't get disheartened by these big lines. Just see the question, and if you know the concept, you can solve it very easily. Okay. So the first question, the question says a supercapacitor. So it is a supercapacitor. First term, with a maximum voltage of 1.6 volt. So you got to know the maximum voltage. Can give 16 farads per gram of capacitance. What will be the energy density and power density of a supercapacitor? For considering device would fully discharge in 60 seconds. Okay, so you know energy of a capacitor. You must have read it in your engineering or science or any other book, also your textbooks also. It's a simple energy is 1 by 2 into CV square. Okay, C is capacitance, V is the maximum voltage or the voltage on which you want to see the energy. It's not only maximum voltage, here it is maximum voltage, so it will be maximum voltage. Okay, so we put the values here, E equal to 1 by 2 into, what is the capacitance? 16 farad per gram. So 16 into what is the V? 1.6 volt whole square. So you will solve it. Just simple. We put the values. You know the exact concept. So just putting the values, you can calculate the energy density. So energy density comes out to be around. I think all the values we are seeing actually. Okay. So for if we calculate it, it will come out around 5.7 watt hour per kg. Got it? It is around 5.7 watt hour per kg. And power. So what we know about energy? Energy is just a capacity to do work. It's just a storage of any form of potential to do any work. Okay. And what is power? So power is energy divided by time. What? So these concepts are particularly very important when we discuss capacitors, batteries, or in case of turbine also. Like if we generate some amount of energy in very less time, so you would say that power coming out of the turbine is very high. So that's how it is related, energy and power. Power is energy per unit time. Okay. So how much energy you are getting per unit time. So if you say 1 joule of electricity. So 1 joule of electricity is just electrical energy that carries 1 joule of capacity. But when you say 1 watt, it is that 1 joule of electricity is getting into that system. Like 1 watt bulb is there, then 1 joule of electricity getting into that system per second, means per unit time. Okay, so that's how we describe it as power and energy. So this is how they are related. Very simple concept. Mostly we guys interchange it or say confuse it, but 1 joule is energy, 1 watt is power. Simply. So we calculated the energy and we divided by time. So what is the time? 60 seconds. So we just divided 5.7 upon 60. So it will come out to be around 0.34 kilowatt per kg. Okay. So this is how the power energy is watt hour per kg, and this power density is kilowatt per kg. Okay. Now the third question. So I think we have solved 2 numericals in a row. So most of you guys will be feeling a bit tense with these numericals. So let's see the conceptual question, then we discuss it, then we go back to the numerical. So I want you guys to grab with open mind, with a relaxed mood. Okay. And it will be better if you don't understand, you can always ask questions. Just don't be shy. You can always ask the questions, and if you have any issues also, you can write in the chat box. So I can read the chat box. If you have any queries, any questions, you can always write in the chat box. Okay. So question 5 is just a conceptual question, and what does it say? A startup company makes capacitor with a working voltage 2 volt. So when you make a capacitor or pseudo capacitor or supercharged capacitor also, so you have to define it the working voltage. The working voltage of any device is always defined. So when you go to market to purchase a bulb, so working voltage is defined. 220 volt, we have to get the bulb with 220 volt. When you go for a motor, that motor 3-phase motor, so working voltage is defined, we will operate it under 440 volt. So that's how we define it. A super company makes capacitor with working voltage 2 volt. To run an e-cycle, the device needs to provide 12 voltage to the motor. Okay, so a device here purchased which is made of capacitor, and it is used to provide 12 voltage to the motor. What will be the best arrangement of capacitor among the following to have the best performance using only 12 capacitor? So we have 12 capacitors. Okay, we have to provide 12 volt voltage to the motor. Working voltage of each capacitor is 2 volt. So if we see uh, capacitors, in case of capacitor, we know that when they are connected in series, their voltage is added up, just opposite to the resistors. You know the concept. Q equal to CV we have derived. I think you must have known it. Okay, C is capacitance, V is voltage. Then you add it to the, then all the voltage will be sum in series. And when it is parallel, then capacitance is added up, but voltage remains same. Okay. So if there are parallel connections, this voltage between these 2 points will always be same. The capacitance get added up. So we have 2 volt working voltage for each capacitors. Okay, and we have to get 12 volt, and we have 12 number of capacitors. So all capacitors are connected in series. If you connect all capacitors in series, what will happen? It will 2 into 2 into 2, 2 plus 2 plus 2 plus 2, all connected in series, and we have 12 of these capacitors. So total voltage will be 24 volt. So you know 24 voltage is greater than 12 volt. So this is wrong. All capacitors are connected in parallel. So if we connect all capacitors in parallel like this, so what will happen? The operating voltage will be only 2 volt. Okay, because all these have 2 volt difference among them. It is not connected in series. And capacitance will get added up. So we don't need capacitance added up. We need voltage, and voltage we need 12 volt. What we are getting here? 2 volt. That's why this is not a good option. Making 2 in series. So what we do if it make 2 in series, 2 into 2, we get 4 volt plus 6 such combination in parallel. So we add 2 in series, 2 plus 2 and plus 6 such combination in parallel. And in parallel what we get? 2 volt. Okay. So 4 plus 2 is 6. So we are not getting 12 volt. So that's why we will cut it. And here it says 6 capacitors in series. So we add 6 capacitor 1, 2, 3, 4, 5, 6. 6 capacitor in series and 2 capacitors in parallel. So we have 2 capacitors here in parallel. We counted 2 volt, 2 volt, 2 volt, 3, 2 volt, 2 volt, and then this. So when they are in parallel, what is the total voltage? That is 2 volt. Okay. So 2, 2, 2, 2, 2, 2, 6 2s. So we get 12 volt. So the correct answer is answer D. Okay. Now we go back to the numerical again. And it's a very easy numerical. These are just conceptual numericals, not very hard. And in the final exam also you will find numericals of this type only. So if you are preparing for the final exam, just practice this type of numericals. Go through the books, the standard textbooks, go through the slides, the assignments. The assignment question will also serve you well for preparing for the final exam. So make sure you are very much conversant with these questions. And if you have any doubts, you are always free to ask them on discussion forum, so that everybody can be benefited from the question which you have asked. And make sure you ask questions are always encourageable, because questions can we can see your perspective also through your questions, like how you are thinking. If you are thinking the good way, or you are thinking on the wrong path, so we can say that no, you have to think in this way, so that you can reach the destination. And even if you are thinking the wrong path, it's totally okay to think, because sometimes wrong path can also lead to a shortcut to some good places. Okay, this is just a quotation. So sometimes you heard the story that some scientists were doing some wrong experiment, but he suddenly discovered a new product. So he was going the wrong path, but he got the result itself. So that's why even if the question is wrong, it's always beneficial to ask. So this is a supercapacitor took 150 seconds to discharge when rate of discharge was 0.5 ampere per gram. This is G minus 1, okay, this is power, so it's ampere per gram. Rate of discharge is 0.5 ampere per gram. The working voltage of the device was 1 volt. So you got working voltage, you got rate of discharge, you got time. Consider nearly ideal supercapacitor. So ideal capacitors is where we can apply this formula IDT by V. Okay, we don't need to integrate, we just multiply it and get the value. Ideal means this, okay, like this type of curve, not this. So for this you have to integrate actually, but for this you just multiply I with dt, you will get the value of area under this curve. Okay, what will be the specific capacitance? So we know that capacitance is equal to I dt upon V. So we have the rate of discharge. I dt is basically I rate of discharge, dt is time, V is working voltage. So if we go for it, 0.5 ampere per gram into 150 seconds upon 1 volt. So if you multiply 0.5 into 150, what will happen? 0.5 is 1 upon 2 into 150 is equal to 75. And what is unit of capacitance? Farad. And what is asking the question? Specific. So you have to divide it by gram. So this is the answer. Answer is B. So I just wrote the unit here by just putting the concept like capacitance is in farad and specific capacitance is in gram. You don't do this type of, because I am conversant with this topic, I can write. You always put these units here, multiply them and get the values. Okay. So the next question. This is a question: if RC circuit is charged by a constant current, the slope of the output voltage versus time graph will be. The slope of the constant current versus time graph. So what is the first thing? Slope is inversely proportional. Slope S is inversely proportional to current. Current is I. Okay. The second one says that S is directly proportional to I. Slope is inversely proportional to root of current. And fourth one says slope is directly proportional to current. So what we see in a RC circuit has this type of slope. So if it's charged by a constant current, and as we increase the current, the value of area also increases under it. As we have seen in the numerical also, we increase the current. What will happen if we increase the current here? It will increase the capacitance. That's how we increase the capacitance. RC circuit for it will increase the slope also. Okay. The slope is directly proportional to the current. Okay, not in unit rate of current. If we square root of current, if we put the square root, then it will be wrong because it increases with directly proportional to the current. Now the seventh question. So which of the following information pertaining to the redox reaction occurring within the cell can be obtained by cyclic voltammetry? So you have seen the cyclic voltammetry curves. How does it look like? It looks like a rectangle. Like we go this, something like rectangle. Okay. I have this cyclic voltammetry. These are cyclic voltammetry curves. Okay, cyclic voltammetry. These are all cyclic voltammeter, not like this, then like this. Okay. So you see, what does it look like? Rectangle. I think there was a question also in previous assignment that how does cyclic voltammetric curve look like? So which of the following information pertain to the redox reaction? And these voltammetric curves very what you say, specifically for reaction, redox reaction. They actually represent the redox reaction, how the reaction is proceeding. So that can be seen through cyclic voltammetric curve. Occurring within a cell can be obtained by cyclic voltammeter. Which of the following? So you see that which of the following parameters. So first thing is potential. Potential is voltage. So you cyclic voltammetric or VI, you can always see the potential. If it is a redox reaction, and since cyclic, cyclic, so you can always get information about the reversibility. If it is broken, then it cannot be reversible. Okay. So this reversibility is also the quantity of electricity. I is there, you can know the quantity of electricity through cyclic voltammetric curve. Net chemical change, this is very difficult to get from cyclic voltammetric curve. Cyclic voltammetric curve can't say what is the net chemical change, okay, but it can say the potential, reversibility and quantity of electricity. So that can be related with the redox reaction. So the correct answer is ABC. In a hybrid supercapacitor device, the output voltage profile corresponds to the given input current. So this is hybrid supercapacitor. You have to first see. If there is a battery, then there can be confusion also. So you have to first read. It is a hybrid supercapacitor. The output voltage profile corresponds to given below input current. This is the input current. Okay, like this. So if we see the output curve of supercapacitor, this cannot be supercapacitor, okay, because supercapacitor Q equal to C equal to 1 by half equal to CV square capacitance, so it something has some slope, okay, CV square, so it will have some slope. A straight line cannot be. So this is also wrong, this is also wrong, so it must be from this or this. So if we see this is also correct and this is also something correct, curve, but the output voltage profile given for the below input current. So you see the input current is increasing and also then it is decreasing. So if it increased by +1, then it is decreased by -1. So it increases and then decreases. So the correct answer is answer B. And this, I think this represents the battery. This very beautifully represents the battery. Okay, so I think this is whole for today's live session. So let me make a recap also, so that those people who joined late can understand. So we had discussion of the previous live session where we discussed about the cyclic voltammetric curves, pseudo capacitors, batteries, electric double layer capacitance. Then we went through Chapman model and Coulombic efficiency. Then we solved numericals also. The first question was basically about slope. So slope, you just have to understand and see the graph also. So that will make you understand what will be the slope. And current versus voltage profile. So there was a numerical also which we solved. We obtained the specific capacitance of RGO. Then we solved another numerical on supercapacitance. We calculated the energy density and power density. Then the fourth numerical was actually about the capacitance, a specific capacitance. So we put the values and got the specific capacitance. The fifth question was basically a very tricky question in which you have to just apply the mind. And if you just go through the options, you will get the answer. Okay. So we just know the concept. If in series, the capacitor is same and the voltage gets added up. If in parallel, the capacitance get adds up, voltage remains same. Then there is sixth question about the slope. How does it vary? It is directly proportional to the current. Then we have which of the following information pertain to redox reaction. So if you see the cyclic voltammetry curve, you can see the current, it is quantity of electricity. Then we see the voltage, potential, and also since it is cyclic, we can also know about the reversibility of the reaction. Okay. So this is all for today's session. Oh, so one more question was there. The output voltage profile correspond to. So if this is the output voltage profile, it cannot be a straight line because supercapacitance 1 by CV square. It always be a polynomial. So polynomial doesn't have a straight line graph. This is also not done. This is also not done. It must be from this or this. If we see if it is increasing like this, see here increasing like this, and then it is decreasing, and it will be decreasing also. So the correct answer is B, not A. But both are almost identical. Okay. That's all for this session. If you have any queries, you can always write in the discussion forum. For any other queries, you can always find me at my email, and any other questions or queries are always welcome from your side. Okay, so thank you guys for the session. We will meet in the next week.